All right. So thus far, we've talked about this idea of evaluating a limit analytically, and it turns out we've got all these nice, cool limit laws, and they're helpful. But it turned out in the last couple of examples we examined, that feels awkward. Anywho, we got the same result of like busting through all of these limit law processes that we would have gotten had we simply plugged our limiting x coordinate into the function in the first place. So I want to take a look at some examples, and I foreshadowed this at the end of the previous video, where that doesn't quite work out here. So off to the side, so I'll often kind of abbreviate DS for direct substitution. We take a look at this function right here. So he may look familiar. We examined him previously in the videos where we were looking at evaluating or estimating limit values using graphs. So we have the rational function x squared minus 1 over the quantity x squared plus 4x minus 5. So if we try feeding x equals 1 into this thing directly, down below we get 1 squared plus 4 minus 5. Uh-oh. There's a 0 in the denominator. That's bad. So, all right. Well, and you may recall from when we talked about this previously, well, if we look up what's happening in the numerator of this bad boy, we have 1 squared minus 1. That's also 0. So we have what you would call, you'll often hear mathematicians and math teachers refer to this as a 0 over 0 indeterminate form for a limit. So, yeah, we have a 0 in the bottom. That's bad. We have a 0 also in the numerator. That's good, because algebraically that kind of gives us a bit of a heads up that, yeah, there's something going on. I'm not going to, drag up a whole lot of algebra here in the interest of time, but yeah, there's something that we can do to kind of clean this up in that sort of situation. So that's what we're going to consider. And it turns out the thing that really drives this is sitting on that handout that I posted with all of the limit laws. There's something it mentions functions agreeing at all but one point. In particular, the point where the limit is what you're considering. So the idea is if we can find a different function that agrees with this everywhere but at x equals 1, then its limit is, the same as the limit of this guy right here. So here's where kind of the magic of the analytical approach ends up coming into play. So, and you might have already done this because I've come across a fair number of students in my, years worth of, teaching that get into this habit. We gave you quadratic functions. Yeah, you're probably going to end up having to factor them in some way, shape, or form. So you may have already done this. So if we factor the bottom of this thing, x squared plus 4x minus 5, however you go about getting it, you end up seeing something like this. So x plus 5 times x minus 1. Maybe you had them flipped around. Potato, potato. Anywho, the top of this thing, x squared minus 1, we've seen before. That's what we call a difference of squares, and it breaks down like so. X plus 1 times x minus 1. Awesome. All right. So now you've probably already noticed this. And again, you got to be a little bit careful with how you do it, and I'll talk us through it. We have a common factor of x minus 1 in both the top and the bottom of this thing. Now, the algebra student in you probably says, well, I'm going to cancel them, slash, slash, and they're gone. I get that. The catch is, in calculus terms, you can't just get rid of them, because if you're thinking of this as a function, with these guys here, this function is not defined if x equals 1. If you cover those guys up, the resulting function is defined for x equals 1, so there is actually a bit of difference in terms of the functions involved. However, thanks to that theorem that says that if functions agree everywhere but at the target point, yeah, we can safely get rid of those guys. Again, the functions are different, but in terms of the limiting behavior, that theorem says they're going to behave exactly the same way. All right, and I'm being a little pedantic here, but just for the sake of completeness. So we have the limit as x approaches 1 of now this adjusted function, x plus 1 over x plus 5. Now you may notice at this point, well, maybe we could try that direct substitution thing again. And lo and behold, this little algebra move kind of got rid of the problem in the denominator, because now if we plug x equals 1 into this thing, we get 6. 6 ain't 0. So this thing's defined, and we're perfectly okay just to plug in x equals 1. Instead, we get a 6 down below, we get a 2 up top, and that gives me a resulting limit value of 1/3 once I reduce the fraction. As you will hopefully recall from when we talked about this with the tables of values, yeah, that's what our numbers were getting close to, was we kept shrinking in on 1. So, great. So, yeah, that's kind of the key idea here, is if we can do some sort of algebra trick to rearrange the limit to get around this 0 over 0 thing, then there's probably something that we can take a crack at to handle this. All right, let's take a look at another example. All right, variation on a theme. Another rational function, quadratic over quadratic. You might start like trying to jump over some stuff, but just in the interest of being careful here, let's try that direct substitution thing first. It's generally students' favorite way to handle things like this, and if it works, it just gets you out of an awful lot of trouble. Unfortunately, yeah, here 2 squared is 4, minus 2, minus 2, 0 down below, that's bad. Up top, 2 squared is 4, minus 2 times 2, 4 minus 4 is 0 in the numerator. That's good. So awesome. Now let's try breaking this thing down. Again, we've got quadratics, so let's factor and see what ends up happening. All right. So there's not much we can do with this except you'll notice both terms have a common x. So let's slurp that guy out to the front, and then we're left with x times x minus 2. Well, there's what's causing the 0 in the numerator. If you want to pause, take a moment, and work out how to factor this thing, that's fine. I got x minus 2 times x plus 1. Again, if you had them written the other way, tomato, tomato. All right. Now, again, if we didn't have this limit out front, we can't just cancel and say that's the exact same function, because we're sort of getting rid of the problem where this thing isn't defined if x is equal to 2. But as far as a limit is concerned, it's okay because of that result from our limit laws handout. So slashing, prices, they're gone. All right, so now all we're left with is an x up top and an x plus 1 down below. There's no longer any trace of badness, so to speak. The division by 0 issue is no longer a thing if we do that direct substitution. Equals 2 over 2 plus 1. So this time around, instead of 1/3, that's one of the ugliest 3s I've written in the last 5 minutes. So that's moderately better. At least it can be, identified as a 3. So 2/3 is our limiting value in this instance. All right. So I want to play around with this example ever so slightly. Give me just a sec. All right. Blink and you may miss it. Not really, but same function in this instance, but I have tweaked the actual x coordinate that we're approaching. So that's going to change things up. I mean, maybe if we just plug this in directly, we don't have a 0 denominator, and all is right with the world. So if you've taken math classes before, you probably know that's not the case. But if I feed x equals -1 in here, -1 squared is +1. Be careful if you just do that in your calculator. You really need like parentheses, like -1 squared. If you do that, don't just write -1 and put a square because of the way the order of operation shakes out. +1 minus 2, and then up top, I'm being a little more careful than I have been. Like I said, I wanted to point out make sure to put parentheses around stuff if you square it directly. Anyway, so we get a 0 denominator. That's bad. So up top, we get +1 minus a -2. So we've got 1 plus 2. We get a 3 up top. Yeah. It doesn't look like what we've done already. We don't have that 0 over 0 indeterminate form. Yeah, as it turns out, when something like this happens, we really need that 0 numerator. So that way there's kind of like a struggle to see what ends up winning out. The division by 0 trying to like make things explode versus, this thing in the numerator trying to, press things down, so there's like kind of a bit of a control issue. In this instance, this is not doing anything to stop our denominator from going kablooey. So as such, this limit, as it turns out, does not exist. So again, if you were having to like put this into web work, DNE is kind of the common thing. We'll talk more about what's making this happen later on, but for now, you can kind of take a look at this. We'll justify this more fully again later on in the week, but for now, if you end up doing a direct substitution and get a non-zero over zero set up here, that's kind of a red flag that the limit doesn't exist. And again, you could check this by like looking at a graph or trying a table of values as you get close to the pointing question. All right, so I wanted to take a look at some things that aren't just polynomials and rational functions, but this video is running on a bit long, so keep on watching.